Hey everybody, back for another video here. We've got this one plus one more to kind of get us through the content. This one's going to focus on energy, which is a really big topic, and it was a really big chapter if you guys remember. But here's basically kind of the rundown of what we did. Remember that energy is measured in joules. I'm sure you guys remember that. But when in doubt in this chapter, if you were looking for a unit, it was probably joules. We started with work. Then we did KE, then we did work kinetic energy theorem, potential energy, conservation of energy, and power. So we're going to go through each of these topics just quickly to get you thinking about everything that you should be thinking about, and then you can kind of dive in and work some of the review problems. But here's kind of the general idea for work. Work was just force times distance. Remember, you'd plug in like a net force here if there was friction involved or something like that. And if you had like a two-dimensional problem, something like this, remember that it's only the force that's in the direction of motion that does work. So if this were like a suitcase being pulled at an angle, you would have to figure out the force down here, this parallel force, and then plug that in up here to see how much work was being done on the suitcase. So that was kind of work in a nutshell. Kinetic energy, pretty basic. There's the equation measured in joules still. Remember, masses always get entered as kilograms and velocities as meters per second. Other than that, those are pretty straightforward plug and chug kind of problems. Work kinetic energy theorem. This one was a little bit more involved, but this was a big connecting piece. So this is something I think they could throw at you in those two questions. But it basically just said that a change in kinetic energy was equal to work. And so we had these weird equations that we wrote out this way, like where we could solve work based on the kinetic energy theorem, or sorry, the kinetic energy equation, or we could solve kinetic energy based on the work equation. So they were kind of interchangeable here. This kind of assumes, these equations assume that something starts at rest or ends up at rest, but these were the general ideas. This is kind of the big point that I think makes this a possibility for the exam, is that you can combine a couple topics, and this theorem allows us to combine forces and energy. So like here's energy and force all in the same equation. And so that's kind of a big one. This could tie in friction and energy and that sort of thing. I think they're going to definitely be combining topics. Since we're only getting two questions, they're going to have to. And so I think this could be one of those avenues. So just something to keep in mind. Potential energy, remember we had two different types. For the most part, pretty straightforward. Gravitational potential energy. Not much to go over there. I think you guys know what you're doing. Elastic potential energy, if you remember, if we involve springs or something like that. Then we've got a couple new characters that pop up. You've got spring constant here, which is newtons per meter. This was kind of described as the toughness or the stiffness of like the spring, how tough it was to stretch it or compress it. And then we have X, which is just how far the spring gets stretched or compressed as this thing goes on. So these are all going to kind of build together for this conservation topic that's coming next. But keep these in mind as you go forward. If you see a spring, certainly think that you could use this equation. You could possibly look at a spring. This as well, if you guys remember Hooke's law, that would be a possibility for a spring also. All right, so conservation stuff. This, I think, is the biggest topic of the chapter because it combines so much stuff. I hate to say guarantee, but I would put a big bet that one of the questions is going to center around this, conservation of energy. Specifically, we talked conservation of mechanical energy, which just deals with KE and PE. So just kind of a quick review there. But just the quick run through, if you have this object that's sitting on top of a hill, you certainly have stored up energy. And as this thing goes down the hill, at this point you have both types of energy. And once you get all the way to the bottom of the hill where it's traveling the fastest, it's now just KE. So if you remember, we kind of worked these problems like this to start. And you look to eliminate. So like if this thing were sitting on top of the hill, there would be no kinetic energy initial. or if it makes it all the way to the bottom of the hill, there's no PE left, so we would actually go through and slash those out before we would break down these equations. So think in terms of that, eliminate what you can. But that's the general idea here with the conservation of mechanical energy. Remember, it all has to be accounted for. You can't create or destroy the energy. So if you have 100 joules up here, we can write that in. Then down here you have 100 joules that show up. It can be converted. It can't be destroyed though. So you can kind of trace it all the way through. We did kind of a falling object example too. So if this were a ball and you have 100 joules of energy up top, you've got 100 joules of energy by the time this thing reaches the ground as well, starting off with PE, ending with KE down here, and that sort of thing. Complicated scenarios, they're going to combine topics for sure. They have to with just 2 questions. So sometimes they come up with really weird scenarios. So like maybe they park an object on top of a hill and then they've got a big spring down here at the end, and they have this thing go down the hill and it comes down here and it compresses the spring. So they combine a lot of different topics here in terms of, you got GPE up here at the top, and then you've got KE down here at the bottom, and then as this spring is going to get compressed, you've got EPE over here. So just kind of stick with your guns, transfer the total amount of energy to each of these scenarios, and then use the individual equations to work it out or describe it. You guys will have to do a lot of describing as well, but just use what you know. They could every once in a while they'll put like an area down here and they'll say that there's friction right there, and so that's where something like work kinetic energy theorem would kick in. So work equals KE down here, so that you could figure out the force of friction and then figure out what it's going to do to the overall energy. So anyway, that's conservation. That's the biggie. Spend time reviewing these problems, thinking about these scenarios, definitely understanding this concept, because like I said, if I had to bet, I think they're going to hit you with a lot of questions based on this. Last topic was easy. Power. It's just the rate at which work gets done. So power is just work divided by time. Remember, it's measured in watts and that sort of thing, just in case they'd have you do like a little spin-off, maybe give you a big problem up here and then ask you something about power or that sort of thing. So anyway, review this. Let me know if you guys have questions. Hope everybody's doing great out there.